The broadcast is now starting. All attendees are in listen-only mode.
Hey everyone, good morning. This is Meher, and what we'll do is we'll just wait for a couple of minutes so that we have everyone who have signed up for the session, and then we'll quickly get started. So let's just probably spend 1 minute for everyone to settle down across platforms. All right, we'll get started in about 30 seconds. So just hold on. All right, I think so. Let's get started. So welcome everyone, and thanks for joining the session. And let me begin by giving an introduction about me. So this is Meher. I've been working with Accolite for the last 1.5 years, and I have over 10 years of experience building web application, architecting them, and also developing them from a product standpoint. And when it comes to AI, it's something which is very close to me. I'm really passionate about it. I love fiddling around with neural networks, writing some code. But some things that I was always fascinated about was how does it work all under the hood? We know we can use a lot of libraries like TensorFlow and a lot of advanced frameworks. But what happens in the simple idea of a neuron, and how does it then scale up and learn so many things just by training? And there are so many keywords that are thrown around like gradient descent, then slope, cost function, feed forward, back propagation, and all that stuff. But what I'll do is I'll keep this really beginner friendly. So even though or even if you guys know a lot of advanced concepts about building neural networks, etc., it's going to give you some interesting insights, and probably you can help others who are beginners in the chat asking questions and help them out. And also just to give a shout out, so for example, if you're really interested in advanced concepts of neural networks, we have covered that in the past. And Priyanka Palshetkar, she had her, I think, 3-part series on advanced artificial intelligence and neural networks series on Accolite. You can find that on LinkedIn and on various other Accolite pages. So let's get started. So what is the idea of neuron? So I think I would expect all of you to have a very fresh mindset. Like, forget about what you have heard. Let's start from building a very clean mental model, and let's build some intuition around it before we start coding stuff. Because coding is pretty easy. Because, for example, if I tell you an algorithm, you go about writing it, boom, you're done, right? But this session, see it as a way. For example, let's take an example of bubble sort. Okay, let's say you don't know it, and instead of telling you how the algorithm works, I show you a visualization. You can see how the pieces are moving, what is getting compared, how it is getting shifted, and then you get an intuition. Okay, this is what it's doing. Probably I can code now. So I think we are going to take that kind of approach. We are going to learn by taking small steps and then applying it on coding. And when it comes to coding, what I'll do is I'll quickly switch to show you guys what the coding setup is going to look like, because later when we are looking, understanding the slides in terms of what Neuron does, how it works, etc., I would not want to get distracted by telling you like this is the code structure and this is how I've done it. So I'll just quickly take a detour. I'll show you how the code is structured here. So this repository, you can find it anywhere on GitHub, and we'll be posting details about this. So this works pretty in a simple way. I mean, this uses vanilla JavaScript. I'm deliberately not using any frameworks of any kind. So you have your plain JavaScript. So for example, the entry point is 1.html 2, 3, 4, 5, and I've named them in such a way so that this is how the progression goes. And similarly, the JS files are also named in this way. I would not recommend to use such kind of naming convention in your production code, but yeah, this is just to simplify so that anyone who picks up this code base, they can just quickly get started. So you can just directly open this HTML file. You don't have to install any npm install commands or pnpm install, etc. No dependencies, nothing. And you can just open HTML file, because I've loaded all the dependencies here and I have imported them. Also in this code base, what I'm doing is I'm using P5.js for some visualization so that we get to see what we are doing rather than just looking at the code. So P5 kind of is a nice library that helps you play around with canvas on HTML. There are other libraries like 3JS, D3, etc., but they are very advanced. So I just wanted to keep it really simple for you, so that even if you want to play around with this library, you don't have to spend time understanding the concepts of canvas, etc. But you can completely ignore it. All the code is completely separated. So your visualization aspect and the actual code which does the thing is completely separate in all of these files. So now let's jump to the slide. All right. So I think I just wanted to have this slide as an icebreaker so that we start from somewhere. So you have your three big circles: AI, ML, and your deep learning. And I'm sure you guys already know what AI, ML, and deep learning is. So I'll just quickly move over to the next part. And this is where we are going to play around these two concepts of regression and classification. So in regression, what, as you can see from the image, is predicting what is the line that probably overlies your data. And you kind of predict, for example, if you have a data set which is spanning like this, for example, on your x-axis, you can have temperature. On your y-axis, you can have number of sales of ice cream. So for example, if the temperature rises, does the sale of ice cream improve or decrease? What happens? So you can plot your data like this, and then you can say, okay, there is some relationship which I can create by having this sort of a line. And classification is where you want to basically apply labels to your two data sets. It could be A or B. It could be like, let's say petals of your different flowers. You can look at the length and width, and then you can say, okay, this is where the dividing line is. If the length is this much, width is this much. Basically, yeah, you get the idea. So let's move on to the idea of neuron. So neuron is basically a simple function. There's a processing that happens in it. It takes an input and it puts out an output. So let's take a very simple example of a weighing scale. Okay, so weighing scale basically gives you some information. It can basically give you information in pounds, or it can give you in kgs. But there is some calculation that happens which basically does the conversion of kilos to pounds. I'm not looking at a weighing scale in the true sense where you stand on it and it gives you the weight, but in terms of a conversion of your kgs to pounds metric. So there's a linear relationship. For example, if the kgs increases, the pounds increases, because that we can see here. This is the relationship. The metric value, which is the multiplier, is 2.2. I think it's 2.204 or something. So we understand that this is a simple relationship. Now let's say, okay, before we go that, now let's say we don't know this value 2.2. What can we do? We can probably make a guess, and we can have someone who knows the answer. Let's say a friend of yours who knows this conversion value. He tell us whether we are high, whether our guess is high or low. So let's do that. So let's say if we try to predict the conversion value, let's say we take 20 kgs and my guess is 6, then the prediction comes out to be 120 lbs. So the target value is basically 44 lbs, right? Because the conversion value is 2.2. So our friend tells us, okay, this is really high. You need to probably go lower. And what we do is then we say, okay, now my guess is 4. How is that? So your friend says, no, it's still really high because the target value is 44 and you are saying it's 80. So let's take a dramatic step now. What we want to do is we say, okay, 1.5, because you have told me it's high twice, so probably I should take a big jump. And that's when I say 1.5. And your friend says, no, it's low, because prediction is 30 and the target, or basically the actual value, is 44 lbs. We again refine it. This time we say, okay, let's go to 2.5, because we jump from 4 to 1.5. So at this point, what we have done is we have said, okay, 2.5, how's the prediction? So your friend says, no, this is still not right. You are high. Your guess is high. All right. So at this time, we do some refinement, and it probably goes on for some time, and we end up at a value of 2.2. And your friend says, okay, now you are getting somewhere. Now this is the conversion value. So this is somewhat, in a very big sense, what a neuron does. Because the way your friend was telling you the answer, and he was guiding you whether it is high or low, a neuron learns in a very similar way. Because what we give to neuron is something that is known to us. And then we say, neuron, okay, make a guess. And every time it makes a guess, we correct it. We tell them, okay, there's an error. So in this setup where your friend is telling you, it's a very vague suggestion when he says high and low, because it's binary. It does not tell you how much high is it or how low is it, right? I could have started with a guess of 20 or 30, right? And if my friend is just saying high, I would probably start like 19, 18, something like that, and it would take me a long time. So so that's the idea. So what we really need to know here is that we looked at we are looking at something called as error here. If you notice that right now the error is 0 because the guess is exactly same. But if you look at the previous slide, when it was 2.5, the error was 6. And if you look at the previous slide again, the error was minus 14. So there was some fluctuation in the error which we were not accounting when we were guessing, because we were just making a wild guess. So if we look at the slides again, the error changes every time, like, and the error is nothing but your prediction minus the target. I'm predicting 120, and what I'm supposed to be saying is 44 lbs, and the error is 76. And every time the error changes. So is there some way we can take this error and guide our guess? Wouldn't that be amazing? Because let's say if your friend, instead of saying high, low, what if he says it's very high? That means I know from, if I made a guess of 20, I probably need to make a guess of, let's say, 10 or something. I need to, like, half it down or go quarter or whatever. And if it's very close to the actual answer, what if your friend says you're almost there? In that sense, you can make a minor adjustment. That's where the error kind of helps us, because we know the answer, and that's what we are doing in practical scenarios. We have a lot of data set, and we know what X and Y map to each other. Why not use that and make it map to work for some data set for which we don't know the answer? Okay, that's the whole idea of getting things to learn, because these are some things which are really easy for humans but really difficult for computers. I mean, it's very, very hard in some of the other problem statements. So now let's see how we can basically take this error and guide us. Okay, now there's going to be some equations coming in, but I'm sure you guys will follow it through. Not too deep, not too deep, and I'll really help you out here. Don't worry. So when we were making the prediction here, so this we were taking the value of x and we were multiplying it by guess, and we were getting something called as y. So if we equate guess as m, okay, and I am using this m because that now we are moving little in this sense of the standards which are used in equations, etc. So we want to be stay close to the mathematical way of using it because that's what you're going to see it everywhere. So your y becomes some guess which is m multiplied by x, right? And we want to and yeah, so that is how your prediction is being done. Now let's look at how do we get the target. Target is, I mean, the target word is kind of a little confusing here because that should be some called as something as known answer or something. But again, this is a terminology which is used a lot in the text, so we will stay close to that. So what target here means is what is known to us. So let's say if my guess is m, okay, stay with me. If my guess is m, then some value plus or minus will be the prediction. This is what this means. That's it. M plus delta M. Okay, stay with me here. So whatever I have made a guess, let's say if my guess was 20 plus actual answer is, let's say 2.2. What do I need to negate from that? 17.8. So my delta M is going to be minus 17.8 if I got that maths right, right? So this is basically your actual answer. Guess plus or minus something is going to be the answer. This is the equation for your answer, m plus delta m multiplied by x. And if we look at what was error, what we did was we were taking prediction, then we were saying subtract it from the target. That kind of gives us what the error is. And if the error is 0, that means our prediction is absolutely right. And you can see that in this equation as well. So if our prediction, which is delta, if m here is absolutely right, in that case, delta m becomes 0 because you don't have to nudge it in any sense, right? So this equation, if you're finding it difficult, you can just play around, work it out. I think it'll really help you out. But let's just move on here. So error is equal to your prediction was, the equation for prediction was y here, and target was t. So error is equal to y minus t. And if we expand this equation, there's nothing mathematical or something complex going on here. We're just replacing these values with whatever y and t means. We get this equation. And if we do the expansion, some of the terms cancel out, and eventually you end up with minus delta m multiplied by x. And what if we rearrange that, what we get is delta m is equal to negative error by x. And at this point, you can probably say I could have done target minus prediction, the negative sign would have gone away. But I'm using again this because it kind of prediction minus target kind of relates very remotely with how your derivatives are done later on in the calculus. But yeah, that's how it goes. So this delta m basically tells us that if I take the error divided by x, what was x? X was the input, and I apply a negative sign to it, that's how I know that delta m is what the answer is going to be. So yeah, there you go. All right, so let's take this example and see if that equation works. So 20 kgs, this is x input multiplied by 4. 4 is m, 80 lbs is y, okay? And target is 44, error is 36. We did the simple subtraction here, 80 minus 44. So what our previous equation tells us is that delta m should be negative 36 divided by 20. And when you do that, your delta m value is minus 1.8. And if you subtract minus 1.8 from 4, you get your value of 2.2. And then, yeah, that's how you get it. So now let's look at the same thing. And if we represent that, So yeah, you can see this. So we have represented the same thing. So this blue is basically the dot which stands for a particular value of kgs to lbs. And what we have done is this purple dot is something that is our guess. And every time I reload this, the guess is going to change. But the way we have calculated delta m by doing that division of error by error, error by input, in one step, we get to the answer. And this is somewhat related to how it is used in linear regression. So now let's quickly move on to it. So what we did here was a simple method of learning by refining the slope of the line. I know the slope of the line has come into picture now, but could we classify using this process? Maybe, maybe not. So, all right. So I want to show you the classification example as well, because at this point we have corrected an error for 1 point, which is this blue dot. What if we have 2 points in the space and we want to say, okay, you kind of find the error in, reduce the error between those 2 points. So this is a very simple example, which is an extension of what we did in this bit. But what we are doing here is we have taken 2 data points. And what we are doing is we are finding from the guess, we are finding the error, and we are adjusting the error for this line. And by doing this, we kind of get a classifier-like model. I would not say this is a classifier, but for a small 2 data set or 3 data set, it can work out well. And now let's look at how we have done this code so that we just kind of get a feel for it. So this one is 3. Okay. So if you look at 3.js, so we have done the similar thing. So what we have here is we can ignore the setup and draw function. Let's look at what the perceptron is doing. So we start with some random values. So this is our input. We have taken some random value from the data, and the data looks like this for 0.1 and 0.2. Let me just remove all of this. And in this, you can see that we have input set as data, some random value for the data, target as some random value for, again, data. And let's ignore the learning rate right now. But in terms of prediction, what we were doing with LBs and KGs was we were saying, take the current value and multiply it by input. And the error was basically your target minus prediction, or we could have kept it other way around also. And our delta was basically error divided by input. So I could have done that, but in this code, just for simplicity, I have, I think, eliminated that negative sign for you guys. So even this works. So now the current value, basically current is nothing but a guess which we did on the top, which is a random number which we have taken. So what we are doing here is current plus delta and multiply it by learning rate. So if I don't multiply it by learning rate, what is going to happen is it is going to jump like this, because at every step it is going to fix the error for the blue dot, and at every step it is, and the next step it is going to fix the error for this red dot. So it's just kind of jumping around between two. It's saying, okay, this is the right answer, this is the right answer. So what we are doing is every time we find an error, we just say, okay, so let's take it here. So what we are doing here is basically every time we find this error, which is 1.8, which directly takes us to the answer, we are saying, okay, take some percentage of it. Let's say 10% of this, and then move rather than directly jumping, because now we have 2 data sets. So that's what we are doing over here. And it kind of plays out really nicely if we just add the learning rate and we see how it kind of just moves a little bit here, a little bit there, and then you can kind of create a classification. Okay, and yeah, something. So yeah, why I'm saying that maybe classifier is because if I just make this data something really more rich, and something like this happens, right? You see that it's not behaving the way it's supposed to be behaving, right? It's thinking that the red dot is coming here. But if you try to see what it's trying to do is basically every time it's finding one of the data set, it's reducing the error for that. And because we have more data points here, it's just kind of leaning towards that and it's ignoring this point altogether. But you can probably play around with this and see for how many different data set it works. But definitely we will not call this a classifier. That's why it's maybe. All right, now let me pause this so that does not trouble the browser. Let's move on to the next part, which is, so we were saying, okay, I just said here, not we were saying, I just said here that we were refining the slope of the line. So the slope of the line is, okay, this M is basically the slope of the line here. And why it is really helpful is because this M was really helpful in telling us how far or how closer are we from the error. Okay, and let me do one thing. Let me come to this part. All right. So let's add a slider. So this is y is equal to mx. So y is 1. If I say 2.2. Now this is a line which we have plotted for the kgs and lbs equation. So this, whatever is multiplied by m, you see how it kind of impacts the value of y. Let's say if I make the value of m as 1, then for a value of 2 for x, the value for y is also 2. And as you can see, that slope it just kind of gives you an idea that there's a slope here. And it's kind of in literal terms taken it mathematically as well. So you have a slope, but there are a lot of other concepts which, not concepts, I mean to say a lot of different ways you would want to calculate your slope. For example, I think I will not take that example right now, but I think I'll just move here because I think I have it in the next slide so that we'll learn it intuitively. So I know we are going into slope and gradient descent, but again, just keep a very clean mind and clean slate, and I think we'll just get through it. It's just fancy terms for doing some simple stuff, but I think building an intuition is really important here. So this is, I just wanted to give an example of slope warning, how we humans see slope as. We see it as some sort of steepness. It could be like downwards or upwards, but we see it more in terms of incline, but that's fine. So let's look at this part. So this is basically English language representation of slope. So for example, if you have this line, and how much are you rising? You're rising 3 steps from here, and then you're on the x-axis, you're moving 2 steps. Then let's say on x-axis again, you're going 2 steps, and then you're rising again 3 steps. 3 steps, every step is basically each of the block. So this is basically your slope. How much your y is changing with respect to how much your x is changing. It's also said as rise over run. So for example, let's say if you're at the bottom of the hill, then let's say if the steepness is like 40 degrees or 60 degrees, then the slope is high, right? And if it's downward from the hill and it's like very steep, then you know that the slope is negative. So that's the idea, how much of the y is rising with respect to x. And you can, let's just jump back again to this. I think, did I close that? No, it's here. Okay, yeah. So yeah, so this is basically your slope. So how much is your y rising? So for example, if I make the slope really high, like 6 and 7, that means, let's say if I make it 7, when I'm saying slope, but just try to think in terms of, if I make a small step in x direction, then a huge step is taken on the y direction. And that's what your y value is basically. Y is some multiplier of x. So that's where your slope is. And slope kind of really helps you in understanding how much you need to reduce your error in number of steps. All right, so let's move on. So if you don't get, again, confused by equations and stuff, but this is what I've been telling you. So how much vertical change is happening with respect to how much the horizontal change is happening. And the easiest way of calculating slope is, for example, you take some point instead of calling it a line, let's say some point in the hill and some point on the ground, and you find, you just, let's say, okay, the hill might not make an example here because we'll have to consider the theta or the angle here. But let's say these are some coordinates, GPS coordinates, latitude, longitude. You take the y, subtract them, you divide it by x, you get the slope. And slope really tells you how steep something is. And in terms of angles, tan theta, but let's ignore that. So this is a way of finding the slope. Now you must be thinking, why are we caring about the slope? Because slope is very much an important concept in trying to understand how neural networks or even a neuron works. So again, it's going to be a big jump, but stay with me here. With respect to lines, it's easy to find slope, but when you have a curve, then it's kind of a little difficult to find the slope because then you're not accounting for all the points here. You might say that, so for example, if you look at this pink line, it might tell you that the slope is 45 degrees, let's say. But in reality, if you're standing here at this yellow dot, you will see that the slope is not 45 degrees, right? So this method of finding the slope, which is y2 minus y1 by x2 minus x1, is not really useful. And that's where your calculus comes into picture. We'll skip over the calculus, but the idea of calculus is that whatever 2 points you are taking on your line, you kind of just start reducing it. And stay with me here because this will all make sense when we look at why we need the slope itself here. Because if we try to reconnect the idea of slope, so whenever we were making the guess was the slope there, because we were multiplying it by x and then we were getting the value of y. And how much change we were making in the guess or the m value was really helpful in coming at the right answer. And that kind of works when you have a direct linear relationship. Let's say you have, okay, let's go to gradient Desmos again. And this works really great for, let's say you have some data which has one-to-one relationship. For example, kgs to lbs, Celsius to Fahrenheit. You can make Neuron, which can make a guess, etc. But what if your data kind of lies here? Okay, and you can also see, if you want to see a practical example, let's say you have planets, right? You have sun, planets are spinning around. The velocity of the planets is not constant at every point, right? As soon as it comes near the sun, it kind of increases, decreases, and a lot of phenomenal things happen. And if you try to plot them, like how the velocity is changing, how etc., then you're not going to get a straight line, because straight line is a very linear relationship, and not everything in nature or data is so straightforward or like one-to-one mapping. Like you multiply something by some value, then you get the y. It's always combination of a complex relationship, and that's where we want the neural networks to, yeah, and that's what we want our neural networks to learn, because linear equations, we can solve it pretty easily, right? Because if we know the formula, we can just write it out. And even if we don't know the formula, and that's what the neuron is going to do here, is basically make the guess, we can again come to an answer pretty quickly. Because if you remember, for a linear equation, we got the answer, which was minus 1.8 pretty easily, because the relationship was very linear. So with just one step, which is like, take the error, divide by input, you just take this value, subtract it, you got the relationship. So even without me knowing or the computer knowing what is the relationship or the multiplier between kgs to lbs, we were able to get to this value. So now let's quickly move forward here. And all right, so calculus. This is something which I'm going to keep it for you guys to go through it. There's a lot of text, but this is going to help you build the intuition of why it comes into play. And I'm not going to go through explanation, but the intuition again here is that same. Slope of the line, but slope of a curved line, because your data is not always going to be linear. And that's the whole idea. We need calculus help us reduce the errors in such scenarios. Because in terms of, yeah, all right. So you can go through this, and if you have any questions, you can always reach out to me. And yeah, I've put in some equations, but yeah, this is just to bring out the curiosity of why you need calculus here. But because calculus is going to be another series altogether, so I'm not going to take a lot of time here. So again, something something to keep in mind is rate of change is where your differential calculus comes into picture, where you're finding derivatives, and area under a curve is somewhere is where your integral calculus comes into picture. But in with respect to neural networks, we kind of are interested in rate of change, right? That delta m, how we want to change that so that we get the right answer. And calculus is, yeah, we can do something infinitely many times with approximation and yet get finite answer. You'll get what this means once you go through those two slides, but let's move on. Perceptron. All right, what is perceptron? So although a title says build a neuron in JavaScript, but the simplest neural network you can create with one neuron is called perceptron. And that's why we have this perceptron here. So far you have understood some intuition for input m multiplied by x is y. I keep on referring back to that y is equal to mx is because that's where the building, that is what the building blocks is. Once you have that great intuition there, you're going to find this pretty easy. So this is again pretty similar. This is your neuron, how it looks like. You have a neuron which is capable of taking one or more inputs, and then it does some processing, and there's an output. Isn't it pretty simple, like a function or something? And to be really honest, your neuron is just a function, but it's all the mathematics and stuff which makes it really cool. So we'll go step by step. Okay, so the step one is to receive inputs. So you have, let's say, two inputs coming into your neuron, which is again like y is equal to mx. You have mx, let's say you can have nx, two variables coming in. And next one is we want to weight the inputs. Now this weight of your inputs is similar to the m and x which we had, the guess which we were multiplying by input. 20 kgs, 2.2 multiplied by 20 is equal to something. This is what your weight is. This is a kind of parameter that we want to tweak. That is what we were doing, right? We were tweaking it when we were getting an error, and we were saying, okay, now take this delta m. So this is your weight for one input, and this is, let's say, your weight for second input. Some processing happens, we'll figure that out. There's an output that comes out. Now, bias. All right, so bias is again, let me not go verbally on bias. All right, so when we had y is equal to mx, now for whatever value of m, I can never have this line look like this, right? Because it always, for every value of 0 for x, the y will be 0, right? So what if my every value for x is not 0? Let's say the relationship is like Celsius to Fahrenheit. Let me see, Celsius to Fahrenheit, what is the formula? 9 by 5 plus 32 is Fahrenheit. Okay, 9 by 5 plus 32. Okay, let's say 9 by 5, okay, 5 plus, what happened? Okay, the line is here. So this is the relationship between Celsius and Fahrenheit. And if you don't have this plus term, you will never get a right answer, because for 0 Celsius, the Fahrenheit is not 0. So you have certain sort of data. These are all your data sets, like, or equations which have such kind of relationship. And this plus kind of lets you, let's say if I make this as m, okay, let me not make it m, will confuse you guys. Yeah, then you can see that when I'm adjusting the b, I can kind of translate it across the axis and make it go above or below the 0, 0. So yeah, so I'll not explain what bias is, but I hope you guys got the feeling that what bias really does here. So in the example where we were looking at kgs and pounds. I didn't want to include that bias because it's pretty intuitive, I guess. So you have a bias and you want to multiply it with some parameter again. And now what we want to do is we want to sum the inputs, right? If you ignore what was the other parts, like, ignore the input one, weight one, bias, weight two, etc., what you're going to see is input multiplied by weight is a very similar relationship to what we had for y is equal to mx. But because we have multiple inputs, for example, input 0, 1, bias, this is what we do. And we want to sum the inputs, okay? Because we want the output to be a single number, which we can kind of play around with, which we can say that, okay, this is right, this is wrong. And now what we want to do is we want to have an activation function. So activation function, I think, is a in-depth concept in itself. I would not go in much detail in terms of why we need it and what kind of magic it does, but it kind of puts your value in some sort of a range so that it's easy to play with the numbers or the outputs that you're dealing with. So for example, in this case, you can have an activation function that basically, let's say if my sum is minus 14.4, an activation function like this will transform this number into something that is between 0 and 1. Okay, and that kind of helps us play around with the values. And activation function is also, if you look at how the biological neuron works, just to give you guys an intuition, for example, not all the neurons fire at all the time, right? There's a certain threshold at which a neuron fires. Let's say you look at food. If you don't like that food, some neural connection in your brain are not going to fire up, right? If you look at pizza or something like that, neurons will fire. So there's some threshold, and it's this activation function is kind of a representation of that. If you look at in true biological neuroscience way, it does not equate 1 to 1, but it's a very simplified way of dealing with that threshold, whether or not should I activate or not, right? Because let's say you have 10, 15, 20, 30 neurons, you don't want them always to fire. Like, some neurons will be dormant, some neurons will be firing, etc., so that you get a wide range of outputs, right? So that's what it is. But I would tell you guys to feel free to read more about it, and there are lots of different activation functions. For example, there's a sign activation function. For example, in this case, the value which we got was minus 14.4, so it's negative. So we will say that once we run this minus 14.4 through this function, activation function, and if that activation function is sign function, then we'll say the output is minus 1 or the output is plus 1. So basically, whatever is the sign of the value, you put that to the activation function and you say that output is minus 1 plus 1. Then you have something which is much more natural, like curves and stuff like that. So in this case, what happens? Your value 14.4 will get represented in a nice continuous value, not like plus 1, minus 1 always. It will have 0.1, 0.3, minus 1, etc., etc. And then you have functions like rectified linear unit. I don't want to deal with that right now again. But yeah, so now let's talk about generating the output. So you have your output. So if I put this through this sigmoid function, which we saw is this one, nice curve looking line, what we get is 0.999, something like that value for the output. Now it's pretty easy to deal with it. And so this whole step of feeding the input and getting an output is also called as feed forward. So this is what your neuron is saying, 0.99. But for as humans, we can't make sense of it, right? But how neuron plays around with this is, let's say all these weights were guesses and your neuron is saying 0.99, but let's say for a known data, right? For, let's say, the value of y for this value of x, y, z is going to be this, then you can find the error, isn't it? Just ignore the 17 and bias. And if your 0.5 is the guess, y is equal to mx, and you get this, isn't this your prediction? Right? This is your prediction. And you, for a known data set, for 18, 17, 1, if you know the weights should be this, then you can tell the neuron that you have an error of a particular significance. And we can do subtraction, etc., here and there, and then try to tweak these parameters so that while these parameters get tweaked, we get the correct output from this neuron for the known answer that we have. I hope that was clear. All right, so again, so this is your prediction 0.99 and your error is going to be prediction minus target. How do we get the target? Because we know for 18, 17, and 1, the weights should be A, B, C. Because these were random guesses, we are not going to hard code these values. For A, B, C, we want to start with a guess. And every time a neuron is making a prediction, we are finding the error. And if you remember how we found the delta M from the error, we want basically our error to guide us. We don't want to make random guesses. I don't want to say, okay, now 0.5, now 0.1. That way it will take forever, or it can happen in like just one go. But I'm sure it's going to be happening. It'll take more than forever to get to the right answer. So that's the idea. We want our error to guide us in terms of tweaking these parameters. And if we don't do that, then we are nowhere. Then we are just as good as your neuron is going to be a math.random function, which we don't want it to be. All right, so there's something interesting that comes, which is about squaring the error. So what we want to here do is, when we get the error, we want to square it. Because sometimes what will happen is your error, if you remember, our error had minus 1.8 in that equation of line y is equal to mx. What we want to do is we want to eliminate that minus sign, because it can give you some inaccuracies. And I've made a table for it, and you can go through it, that why we want to square the error. Because let's say if I give network, if the output of the network is this, and if this is the prediction, and this is the known answer that I want from the neuron, then what I get if I don't square the error, or if I keep this negative sign, is that you can sometimes get that the error is 0, which can't be the case. And that's why we do the squaring of the error. And again, so this, all right, okay. So although we are running out of time, we have just 13, 14 minutes. What I'll do is I'll skip this slide, but this is pretty much similar to what we've done with slope. So what we want to do is we want to find the error, and we want to see how much, we basically want the error to guide us in terms of adjusting the prediction. So what you get here is, if you do all this mathematics, is that for this delta M, we get that delta M somehow is related to 2 times the error times the X. And what we have done here is we have just found slope of each of these lines. We can probably have another second session for this in case you guys are curious. Probably leave a comment, let everyone know that we would want to have this, and we can probably dig deeper into that. But this is how we get something like this, delta M, in case when we start to square the error. And rate of change for B, I wish this session was a little longer, but if you have got the idea of how this works, then take this as an exercise and try to find the rate of change for B. And once we have done that, we can adjust the weights. And the step 10 is basically to repeat your feed forward, finding the error, and again, adjusting your weights. Now let's quickly look into the code that basically does that. Before, okay, let me take it here. All right, so this is, I'll quickly spend 1 minute on this linear regression aspect, which is basically what we did here in terms of guessing and making our guess come closer to this. Then we can use, I'm sorry. So what I'm doing here is, in linear regression, we have some sort of a data, and I'm using that same explanation that I talked about earlier, which is y is equal to mx. And we are using some sort of adjustment to make this prediction that where this data lines up. And this, again, if we look at fourth file, you're going to find, yeah, we are not doing anything different. Sorry, this is 4. Yeah, this is 4. So again, we are doing the same thing. We are finding the error, but in this case, what we are doing is we are adding all the errors. And when we are adding all the errors, we are finding the average error, and then we are creating a line that kind of goes very closer to these data points. So in this case, okay, in this case, when we were basically making one prediction, we were directly making a line here. But what if we had like 10, 15, 20 data set? Then we can just find the average error and make this prediction. So every time the whole process that we talked about minus error by x, if we just codify that, we kind of get this output. And this is your linear regression by using sum of all the errors or mean errors. And if we use gradient descent, which is basically a simplified way of reducing all the errors and stuff, we can use calculus to help us do that. But I'll just park this for now and let's look at the code for perceptron. So perceptron code is in your file, which is 6.js. Okay, so I'll quickly spend 4 or 5 minutes and then I'll probably take some questions here. So this is a neuron or perceptron, a neural network with one neuron. So it has, you have your constructor where basically we tell it that you start with X number of inputs. And then what we are doing here is, okay, let me zoom in a bit in case it guys will just help you. All right. So we start with some random weights. Okay, as you can see, I'm taking some random number between for all the weights. So what this means is when I'm creating my perceptron, I'm saying, okay, let's create this perceptron for 3 inputs. Okay, that is X, Y, and then bias. So that's what you're going to see here. Just ignore what is happening in the draw function because the draw function is where we are dealing with the canvas. But yeah, as you can see, I can then create a new instance of a neuron and I say create a perceptron and initialize it with 3 random weights and let this be the learning rate. Or like, whenever you find an error, don't solve that error immediately. Solve that error step by step, like, in small increment steps, because we are not dealing with just one data set. We are dealing with a lot of data sets. So that kind of helps. So we start with a perceptron, assign random weight, and then we are saying that, okay, C is going to be my learning rate. So that's how you initialize it. And then if you remember the step 1, 2, 3, 4, 5, or I think 4, 5, 6, we talked about finding the sum of your inputs multiplied by your weight. So if we just look at this, so this step, yeah. So this step, sum of the inputs, which is basically input multiplied by weight, etc., etc. This is what we have done it. And you're seeing a loop because we're just looping through this weights and input because our input is an array. And what we are eventually doing is we are saying, once you have found the sum, pass that sum to this activate function. And what is our activation function? So in this example, I've not used a sigmoid because I realized later on that sigmoid will kind of use a lot of math functions. So I've used a simple sign function. So if the sum is greater than 0, return 1. If it's not greater than 0, then return -1. That's it. So basically that threshold, whether should I fire or not, etc. So these are the 2 functions. Pretty simple. Finding the sum of the inputs multiplied by weight. And if I was not doing this plus equal to, then this should kind of remind you of y is equal to guess multiplied by x. But this is kind of a longer version of that. So this is your feed forward. Okay, let's close that. And this is your activation function, which we call as activate, and train. So in this train, train is basically when we get that error, which was basically what is your desired output minus your guess. I'm sorry, I keep on flipping this value, but it does not matter that much. It does obviously when you try to do calculus, but again, let's just ignore that. But yeah, we are finding the error by finding the desired minus guess. And then this is how we are basically adjusting each of the weights by saying that adjustment to the weight is done by learning rate multiplied by error multiplied by each of the input. I know this piece of code will kind of get your brains to tickle and you'll be like, why does this work? And this is where I would want you to go to this slide, which is the how it is applied to neural network. Because if I spend some time on this, then this would be more than 1 hour session. But this will basically get you the idea that why do we know this value is going to help us adjust the weight, and it is in reality very much similar to how we used this derivation. So if you're feeling comfortable with this, which is how we found delta m should be something divided by x, error divided by x, then you will be comfortable understanding why in this case the error is, instead of divided by input, it's getting multiplied by input, because we are taking into consideration that your cost function is error squared. I know all of this is kind of little can go heavy, but yeah, just stay with that. You have gone through that equation of line finding delta m. You can do this, and so don't worry about that. So I mean, there are two ways to do it. One is either you start by understanding slope, how do you calculate slope, etc., or you can just memorize some of your derivative rules, for example, power rule, chain rule, etc. But if you really want to understand why does it work, why does the power rule say that x to the power n is equal to n to x to the power n minus 1, then you can start spending some time on this slide, because that's what I've done here. I've taken some equation, found the derivative without using the power rule, but just by using the slope function. And you must be again thinking, why are we using calculus? It's the rate of change. The rate of change is really important here to guide us in terms of what should my next weight be, isn't it? So for example, if you are seeing this, isn't this rate of change? You're changing your weights by some minutes. I mean, you're changing by weights by some value. It's like you are driving a car, you see a sign, red traffic sign, and you want to use that input and apply some rate of change on the velocity of your car, right? So this is how we are using it. And why does this whole slope gradient descent come into picture? Because we want the error itself to tell us what should be the next value of weight be, right? For example, let's say you're driving the car, you see a red traffic sign. You're not going to randomly press up, down on your accelerator. You're going to use that value and then guide your pressure on the pedal in order to guide yourself to stop the car at a particular stopping distance. So that is where the whole slope comes into picture, how steep, negative, positive, etc. And that's where the slope goes into the calculus side. So yes, and I think with that, okay, I was concluding this slide, but I've not shown the perceptron. So perceptron, okay. So before I just give you some background here. So I have taken two data sets, blue and red, and this dotted line which you see is the actual answer, and this solid line is what the perceptron is trying to guess. So if I reload, you can see that this is the guess this perceptron is making based on each of the data set. And how I have gotten this data set is basically I've randomly generated it, and you can find that function here in terms of how I have created this data set. It's pretty simple. I think it's nothing too complicated. It just basically take an equation of line, then yeah, we do that. So all right, I think let this neuron do the learning while I take some questions. Let me just see if this session can go for 5 more minutes with the coordinators. All right, so I've got to go ahead. I've been told that yes, we can go a little over time. It will not auto disconnect for you all. So let me take some questions here. So I know overall that we have covered a lot of ground, but trust me, this is a must. So the whole idea of slope gradient descent, why we covered it before we covered the neuron is because we need to have all the tools in hand before we start coding stuff. Because if I have told you that this is the algorithm for neuron, we take inputs, we submit, we do the auto activation function, then the whole intuition and mental model does not come into picture. And I think if the second half of the presentation felt little fast for you or a little hard for you, advanced for you, I would say spend a little more time on the equation of the line, because that will kind of guide you in terms of how should you approach something little advanced. Because linear regression, or the this example which we did where we were using statistical method to solve this problem set, kind of gives you an intuition that how we can use something little more advanced in order to get some answer. All right, so time for some question. Okay, first question is, why is the language JS and not Python, which is more prevalent in deep learning? Suppose I have no idea about JS, can I understand it? Yes, absolutely. So the reason I use JavaScript is so that you can just run it on browser. I can probably host it on some of the platforms where you can immediately run it. And I thought JS is kind of a little more forgiving in terms of how you play around with it. But yeah, the same thing you can do it in Python. And because I was not doing anything related to deep learning where I needed some sort of machine power to do a lot of computation, I just wanted to get the idea across. I thought I'll just stick to JavaScript. And again, JavaScript is also one of my favorite languages, so that's the idea. And of course, you have no idea about JS, but you can absolutely understand it. And I'm sure if you know Python, then you have a lot of love for programming. And as a programmer, you can pick up all the same fundamental concepts of programming in JavaScript. There's nothing that can stop you. How can we know the prediction if we don't know the multiplying factor? So how this works is basically, how can you know the prediction? So you know the prediction by starting with a guess, right? You start with a guess, and of course you don't know the multiplying factor, so you start from some point. You definitely don't start from zero, but you start with some other point. So that's how you start. That's how you get the prediction, right? Because you're guessing it. So your multiplying factor is also a guess. Is there any prerequisite for session other than JavaScript? No, absolutely not. There's no prerequisite, no npm, pnpm, npm install, yarn install, nothing. You just need basic JavaScript. There's a bunch of code for p5.js, which is doing all this nice little animation, which you are able to visualize and see rather than seeing the black code screen. That's all, but you can completely ignore it. And is this webinar related to integration of neurons with AI, ML stack, and web integration, or only built in JavaScript? The whole idea for this was not to make it a complex project of some sorts. This whole idea for this webinar was to get an intuition for how Neuron works, so that when you're working with, if you have not worked with neural networks or libraries, then you feel comfortable about it. If you have worked with neural, let's say, frameworks like TensorFlow and etc., then you know what's happening behind the scene, so that you are able to guide yourself better. Please provide the name of the repository to be downloaded. Absolutely, we'll do that. We'll share it with you through the right channel. I think you'll drop it in your inbox, or I will add the same thing in the slide as well, in the last slide. So you'll be able to use this code base for sure. And I'll probably get this hosted on some of the platforms so that you can access it on web without even running it on your local machine and view the code. So we'll do that. Same question, where will the source code be? Will we use the gradient descent? Yes, we did use the gradient descent, but again, because of time factor, I felt gradient descent needs little more step back. I mean, I could directly jump into explaining the gradient descent, but again, I believe a lot of people are going to be beginners and freshers here, and I just didn't want them to get bombarded with advanced calculus concepts. But we did use gradient descent in this, absolutely. So for this example, we are not using any square of the sums. We are using gradient descent to completely guide it. And I can just show you the code for the fifth as well. So yeah, in this example, you can see that we are using a gradient descent here to guide the learning rate, guide the prediction. We are not using sum of any errors. So in both the cases of training here, we are using gradient descent, and even in fifth, we are using gradient descent. So in this, we are using squaring the errors to find the correct way to draw this regression. And in this one, we are using descent. So yeah, not repeat myself. How have you used bias? I have used the bias in a pretty standard sense. I mean, I started with a value of, I think, 1 or something, or even you can start with the value of 0. So that's that. What are we exactly building? I'm not able to understand what does it mean by neuron. Can you explain it in simple language? What does a neuron mean? All right. I think if you just go through this session one more time, I think you'll get the idea of what does it mean by neuron. Neuron is a building block for building neural networks. With neural networks, you can do amazing stuff like number recognition, which you have seen, that you write a handwritten number on a piece of paper, the computer can guess what the number is. So yeah. In weighing scale, is m is constant term or is varies according to the function? Okay, in that weighing scale example, m is not a constant. It changes. Okay, while we are doing the prediction, it changes because we want to get to the right answer. Because if you look at the weighing scale, it's just a conversion formula for kgs to lbs. And kgs to lbs is kgs multiplied by 2.2 is equal to whatever the value is. So that 2.2 is definitely a constant. But while we are playing, while we are making the prediction, guess, finding the error, etc., that whole exercise of building the intuition, we were kind of using it as a variable. How is neural network better instead of using normal linear regression here? I think it's better in terms of a lot of ways. For example, linear regression can only solve linear problems, but one of the reasons perceptrons or the neural networks were dormant for many years was it was believed that neural networks or the neuron or this perceptron cannot solve non-linear problems. So if I talk about non-linear, I'll just Google it so that yeah. All right, something like this. So let's say if your data set is these two stroke dots, and how do you classify this? Not this one. All right, yeah, this one. So this kind of data set. For example, if you want to classify the minuses and pluses apart, then how do you classify them? And this is also basically called as you can visualize this as a XOR operation, right? And that's where it comes into picture. Basically, what I'm trying to say is neural networks can solve non-linear problem, or linear regression can only solve linear problem majorly. Where are neurons used? Neural networks. Are the neurons in our brain similar to the neurons in the neural network? They are very similar. There's in our brains, there's a lot of biochemistry happening, right? So not everything is digital in our brains. While we are trying to create something which is very similar to how it works in our brains, it's not a one-to-one mapping. So for example, your inputs in your brains are received from dendrites, and you have many of them, and there are so many parts of the brains that we don't understand ourselves as humans, but we have tried to create somewhat a very similar representation of how this neuron or neural network works. For example, if I give you an example that why is it not one-to-one? Let's say if I show you an example of an animal which you have not seen ever, right? First time you open a Discovery Channel, you see a new animal coming up, and probably a week later I show you the same picture, you will be able to recognize that animal, right? But if you do that with neural network, it will not happen. Neural network needs a lot of training. So there are a lot of things, and in a lot of ways your brain neuron works, which is very different in terms of recognition, which these neurons cannot do. They can definitely do recognition in terms of a lot of training and training data. But for example, even if you show a kid a picture of a cat and a dog, and you tell a kid to distinguish cat and a dog, they'll do it immediately. They don't need training, right? So there's a lot of biochemistry happening, but in terms of the way I talked about the activation function, this weights, parameters getting input, for example, in your in your brain, the neurons which are connected, they are connected via axons. So the axons have a layer called as myelin. So a more frequent few neurons fire together, the myelin layer gets thicker and thicker, and that thickness of the myelin layer kind of represents the weight, strength of the weight. So we are finding some sort of relationship in terms of how it works, but it's definitely one-to-one. It's not one-to-one. So is there any build-in function in JavaScript for perceptron or Neuron? No, no, there's nothing. You have to do it everything from scratch, or you can use a library. As fresh as what would be the technologies and platform we will be using? I think you can start with Python, TensorFlow, Keras. You can use platforms like Kaggle to understand it, and Kaggle to play around with such code and get interesting problem statements, and also get learning from a lot of other peers what they are doing. But yeah, what platform to use for the code's output? I'm not sure what that means, but for this code, you don't have to use any platform. You have the browser. Have you used the bias in the? Yes, I have used the bias. Ordinary least square. Yes, correct. Yeah, I have OLS. OLS is basically ordinary least squares. In this one, I have used ordinary least squares. What people are saying is that ordinary least square is another way of saying that whatever error you have in your data set, you kind of square them and then you average it out. That's it. And so that is OLS, and this is gradient descent. All right, I think I've covered a lot of questions, and I think we are a bit over time, so I'll respect time, and if there is any more questions, feel free to reach out and drop comments and notes on whatever platform you are on, whether it's YouTube, LinkedIn, or you have joined directly through go to webinar link. Yeah, there are ways you can reach out. And thank you for joining. And stay tuned for the next session from Accolite Digital. And hope you have a great day. Thank you.